Hi, welcome back to this channel. In today's lesson, we'll see magnetic circuits. There are two types of magnetic circuits, the series magnetic circuits and parallel magnetic circuits. One unique thing about the series magnetic circuit is it could comprise of materials made from different types of materials and dimension, but the flux moves in same path. But in the parallel magnetic circuit, the flux moves in different paths. In fact, the flux in the parallel magnetic circuit, if I have flux file, it equals to file 1 plus file 2 plus file 3 plus up to file n, depending on the materials comprised in the parallel magnetic circuit. In this lesson, our attention will be on the series magnetic circuit. That said, let's see the series magnetic circuit. For the series magnetic circuit, like I said initially, the flux around this magnetic circuit file is unique, so that it's the same, so that the flux file in this magnetic circuit is the same. But the reluctance of this magnetic circuit S is equals to a combination of the reluctance of all the components of the magnetic circuit. That is, S will be equals to S1 plus X2 plus S3 until Sn. Remember that S from our lesson on reluctance is the same thing as L over U naught UR E. So that I can now say that S here will be the same thing as, in place of S1, I'll have L1 over U naught is universal, UR1 depending on the material, A1 plus L2 over the universal U, UR2, A2 plus L3 over the permeability, universal permeability, UR3, A3. It continues this way until the last, which we tag N, which will be Ln over U naught, URN, En. Now we've gotten an expression for S. Let's remember that my e.m.f for any magnetic circuit is the same thing as phi times S. Now, since the magnetic flux, which is a phi in this circuit, is constant, as shown here, here is a magnetic flux. Since it is constant, I can say that my e.m.f will now come from phi times the whole of L1 over U naught UR1 A1 plus L2 over U naught UR1 A2 plus up to Ln over U naught URN En. Now you'll see that we've created a bracket to multiply phi all through. Let's remember that our magnetic flux density B from our last lesson is given as phi over area E. Now that means my e.m.f is equals to, I want to open this bracket and multiply through by phi L1. I want to bring A close here. This will be my A1. I'm only rearranging. I've not changed the equation. U naught UR1 plus phi L2 over A2 U naught UR2 continues this way up to Ln. This will be phi now multiplying with Ln over an u naught urn. In the next point, what I'm going to do is I'm going to replace my file over A1 with B, that is the magnetic flux density. e.m.f equals to B1 over U naught UR L1 plus B2 over U naught UR L2 plus, it continues this way, L2 plus Bn now over U naught URN Ln. Sorry, I should have my 2 here and my 1. Now let's remember from our introductory lessons that our U, the permeability of the material, of the universal material, is equals to U naught UR, and it's the same thing as B over H. That is the magnetic flux density over the magnetic field intensity. The magnetic field, that is the magnetic flux density over the magnetic field strength. Now, if B U naught over UR is equals to B over H, this implies that H is equals to B over U naught over UR. So that in place of U naught, in place of B over U naught UR here, I can simply replace it with my H. Obviously, my e.m.f will be equals to H1 L1 plus H2 L2 plus H3 L3 plus, and it continues this way, the last magnetic field material, which will be Hn Ln. That said, let's see an example that can help us understand it better. An example says a closed magnetic circuit of cast steel contains a 6 cm long part of cross-sectional area 1 centimeter square and a 2 cm part of cross-sectional area 0.5 centimeter square. A coil of 200 tons is wound around the 6 cm length of the circuit and a current of 0.4 amps flows through it. Now, determine the flux density in the 2 cm part if the relative permeability of the cast steel is 750. Let's take let's take the given parameters from this circuit. We have that UR is given as 750. Now the magnetic circuit is a closed magnetic circuit and it's made up of two different materials. The first material, let's tag it as A1, has an area of 1 centimeter squared, 1 centimeter squared, which is the same thing as 1 times 10 raised to power minus 4 meters squared, and it has L1, which is the length, which is 6 centimeter, which is same thing as 0.06 meters, and it has a second part which has A2, which is given as A2 has 0.5 centimeter squared, which is equal to 0.5 times 10 raised to power minus 4 meters squared. L2, which is given as 2 centimeter, that's the same thing as 0.02 meters. Now, with these parameters, we are asked to find the flux density, which is B, for the 2 centimeter part, that is B2. We have to calculate for B2. Now, let's establish some facts. First, I'd like to walk you through my thought process to make it easier. First thing we should understand is what we need is our magnetic field density, which is the same thing as my flux over area. Now, for the flux, we know that the same flux flows through the composite circuit because it's a composite series circuit. It will have the same flux, but they have different area. Now, we've been given the area to be 0.05 or zero point 0.5 times 10 raised to power minus 4. Now, so what we're going to do is we're going to look for the magnetic flux first. With the magnetic flux, we should be able to find the magnetic field density. Now, to find the magnetic flux, we have two unique properties from this circuit. If you look at the question again, we have two unique properties. We have the current I, which will given as 0.4 amps, and also we have the number of turns, N, which is given as 200. Now with this, we should be able to find the flux. Now, the EMF of that circuit will be given as Ni. That is, the EMF will be given as 200 times the current I, 0.4. And we know that the EMF of this magnetic circuit is the same thing as Ni, and it's the same thing as the phi times S. EMF of the circuit is the same thing as magnetic flux times the reluctance. So let's get to work and let's find the reluctance of that circuit. S in that circuit will be the same thing as S1 plus S2. Now let's find S1 first. S1 will come from L1 over U0, UR1 or UR since it's composite circuit times A1 should be the same thing as L1 will given in that question. L1 is 0.06, A is 1 times 10 raised to power minus 4. So L1 here is 0.06 over U0 is 4 times L times 10 raised to power minus 7 times U have been given to be 750 in the question times A. A is 1 times 10 raised to power minus 4. So that S1 from my calculator, S1 will be the same thing as 6.369 times 10 raised to power 5. Now let's calculate for S2. S2 will be L2 over U0 UR A2, so that S2 now will come from the L2 of that from the question is 0.02 over U0 is 4 times pi times 10 raised to power minus 7 times 750 times area for that part, that's 0.5 times 10 raised to power minus 4. So that S2 will now be, from my calculator, S2 will be 4.246 times 10 raised to power 5. Now, S will be equals to S1 plus S2. That's equals to 6.369 plus 4.246. Both of them are multiplying 10 raised to power 5. So that's S equals to 10.6 times 10 raised to power 5. If S is equals to 10.6 times 10 raised to the power 5 Weber. Now, if S is equals to 10 raised to the power, if S is equals to 10.6 times 10 raised to the power 5, we can from there deduce our file. Our file is equals to Ni over S, which is equals to 200 times 0.4 over 10.6 times 10 raised to the power 5. So that my file from here will be the same thing as 7.62 times 10 raised to the power minus 5 Weber. Sorry, S is not measured in Weber. This was a mistake. It's my reluctance. It's per Henry. It's per Henry. It's per H. S reluctance is measured in Henry. Flux is measured in Weber. It will be the same thing as 7.62 times 10 raised to the power 5 minus 5 Weber. Obviously, we can calculate our flux density for the 2 centimeter. We can calculate our flux density for the 2 centimeter part. Now, we know that our flux density is equal to flux over area. That's equals to 7.62 times 10 raised to the power minus 5 over area. That's 0.5 times 10 raised to the power minus 4. For my calculator, this is equals to 15.24 times 10 raised to the power minus 1 Tesla. Or the unit, you can take the unit to be the same thing as Weber per meter squared. Now this is, I can write it simply as 1.524 times 10 raised to the power minus 1 Tesla. With this, we've come to the end of the lesson. I hope you now understand how to work with magnetic flux. I hope you now understand how to work with magnetic circuit, especially the series magnetic circuit. To ensure you receive our next lesson when we create it, please do not hesitate to hit the subscribe button. That way you will be sure to receive our next lesson when we create it. Thank you for staying with us and see you in our next class.